All right, everybody. Good afternoon. Today we're just going to be filming your final exam review for Organic Chemistry 1. So this is the last test you're going to take in this class. Hopefully it goes well. Let's jump right in, right? So the first thing you should know is this exam is out of 400. Your old test, I believe, were out of 300. And then just be careful you don't miss any pages, okay? So fill in your first name, last name, ID, and then jump in. So the first question, it says circle the only compound that will have a quartet in the HNMR. So the first thing you got to know is what is a quartet, right? So let's write this in. Quartet means n plus 1 equals 4. So n equals 3. And what is n? N is the number of neighbor hydrogens. Okay? So all you got to do is look through these and find the one that has a quartet. So we'll just start left to right, okay? So this is kind of a time-consuming problem, but just take it slow, okay? So we have a hydrogen here, okay? So this is the first hydrogen we're going to look at in the HNMR. So now I want you to imagine this hydrogen, its adjacent carbons have these H's, okay? And these are all equivalent. So we have 1, 2, 3, 4, 5, 6. Okay, so that means that for this purple blue hydrogen, n equals 6. So the splitting is going to be what? Yeah, exactly. It's going to be septet. So this hydrogen is not the right answer. So that's wrong. Then we're going to jump to this salmon hydrogen here. Okay, so if we look at this hydrogen, okay, or any of these, because these three are equivalent. These three all equal each other. So if we look at any one of these, and we do the n plus 1 rule. So n plus 1 equals what? Find the number of neighbors, right? So this hydrogen is attached to this carbon, which is attached to one carbon, which has one hydrogen. Okay? That's kind of a lot, but basically there's one neighbor. So 1 plus 1 equals 2. And that is a doublet. So that's wrong. Okay. So you know it's not going to be this. This is wrong. Okay. And similarly, this is going to be the same case because this one and this one, these are equivalent. Okay. So then you come here and you're like, okay, let me check this hydrogen, right? The only issue is there's no hydrogen here. So you don't need to do that. Okay. There is hydrogens here, however. And these three are all equivalent, okay? So look at this hydrogen, or this one, or this one. They're all equivalent. They're bonded to one carbon, okay? And that carbon, it has no hydrogens. So it's going to be 0 plus 1 equals singlet. So this is wrong. So that means that this whole thing is wrong, okay? Okay. Yeah, so then we're going to jump to the next one, and we'll just do the same thing here, okay? So let's start here, okay? Let's look at this hydrogen, and let's find all of its neighbors, okay? So this carbon has 1, 2, 3 hydrogens here, right? And similarly, this one has 1, 2 here. So if we look at the splitting pattern on this H, we got 1, 2, 3, 4, 5. 5 H's, okay? So that means that n plus 1 is going to be 5 plus 1, which is a 6. It's a 6 splitting pattern. I don't know why I can't remember the name, but it's not a quartet. So this is wrong, okay? Yeah, so then let's look up here. Let's move to these ones in salmon, okay? So these three hydrogens are equivalent, so you can look at any one of them, but let's just use this for an example, okay? This H is bonded to a carbon, which is bonded to a carbon with one H. So this H, it's going to be with one adjacent hydrogen. So 1 plus 1 equals doublet. So that's not our answer, okay? So then the next thing you got to do is, let's come down here and look at these in this color. So if we look at these, right, let's find, well, first let's establish this and this are equivalent, okay? So we're going to look at this hydrogen is bonded to a carbon, which is bonded to a carbon here with one H, okay? Also, if you go this way, it's bonded to a carbon with two H's. So the neighbors are how many? 1, 2, 3, right? So for this purple one, it's going to be 3 plus 1, because n plus 1, and this is the number of neighbors, equals 4. So that is actually a quartet, okay? So we found the quartet, which means this is our right answer. And if you're actually on the test, just circle it and go, okay, this is like a lot of time you're going to waste. But for the sake of the video, I'll do all of them, so you know. So now let's look at the cyclohexane. Okay, so first thing you need to recognize is all of these positions, right? They all have two hydrogens, okay? So that means that if you do the splitting pattern for any one of them, you can just extrapolate it to the others, okay? So let's just look at this hydrogen here, okay? This hydrogen here has how many neighbors? 1, 2, 3, 4. 4 plus 1 equals 5. That's what? Kinset, maybe? But it's not a quartet, absolutely. So that means that no matter which one you look at, you're always going to get that 5 signal. So this is wrong, okay? So this is just immediately wrong. Here, we can do this as well really quickly. This has H's here like this. Right, so if we do this pink one, this H here is bonded to a carbon with no H's. There's no H's here, none. So this would be a singlet. So if this is a singlet, because n plus 1, so it's 0 plus 1 equals 1, which is a singlet. And this, all three of these are equivalent positions. That means these are all singlets, okay? So that means that this is a singlet, this is a singlet, this is a singlet. Here, there's not even hydrogens, so that's just immediately wrong, okay? Here we have 3 H's, right? So we have H, H, H. But the same issue arises. Like, this is a H bonded to a carbon with no H's. So the n plus 1 here is going to be a singlet again. Singlet. So this is wrong. This is wrong. So then you need to move to the next position, which is here, right? And look at these H's. And same issue. This H bonded to a carbon, which is bonded to a carbon with no H's. So these are also singlets. So this is just wrong, okay? X, wrong. And then last but not least, you can do the splitting pattern on this. Here there's 3 H's, right? But there's no neighbors. There's no neighboring hydrogens. There's no hydrogens here. So this cannot possibly be right here. This is not no splitting. Here you have H, H, and then neighboring you have 2 complex H's. This would be weird splitting. But it would be like n plus 1 equals 3 because there's 2 H's here. So 2 plus 1 equals 3, which is a triplet. Okay. So this is also wrong. Hopefully that made sense. But yeah, this is our answer here. We're looking for the quartet. Okay. So moving on to the next questions, which is the strongest acid? Okay. Immediately off the bat, I hope you all saw this and recognized this is something called a Grignard. And this is like the strongest base ever. Not actually, but, you know, almost. So this is not an acid, okay? Absolutely not, okay? CH3SH, CH3OH, CH3Cl. All of these, let me go on do not disturb real quick. Okay, sorry. Yeah. So back to this. So now we're going to look at these four structures. Immediately between this one and this one, we did this in class a bunch, but SH is larger and more polarizable than OH. So between these two, SH, or not SH, sorry, just S, is larger, more polarizable than O, not theta, sorry. So you can eliminate this because we know SH is going to beat OH. So it's going to beat this one. And then similarly here, SH is going to beat this one because SH is a better acid than OH, okay? So then the last thing you need to look at is CH3Cl. So just draw this out and it'll be very obvious. So hopefully you recognize these hydrogens are on an alkane. They're hydrocarbons. Because this carbon is bonded to hydrogens, but carbon-hydrogen bonds are not acidic at all. So this is not the answer. Yeah, carbon-hydrogen bonds, these are not acidic. This is not acidic bond. So that means that our answer is going to be CH3SH. Okay. Okay, the next question says circle the only ether. So hopefully you know what an ether is. Let's draw out what an ether is. Ether is simply, let me just put an arrow here like this, R, O, R. And this can be linear or in a ring, okay? It can be either. So it could look like this, or it could look like this. Oops. Like that. That's totally fine. These are both ethers, okay? So keep this in mind here. So all we have to do is just identify where do we see an ether. So in this first structure here, this is not an ether because there's not even an oxygen. So immediately knock this out, okay? This is like a nitrogen ring derivative. You'll learn this in organic too, so it's not important. But that's not an ether. This here, what is this functional group? Everybody tell me. This is an alcohol actually, right? Not an ether. So that means that this is wrong. This is not an ether. This, this is just a simple alkane. There's not even like any functional groups at all. This is this hydrocarbon. So I pray that you don't circle this. This is wrong. Okay, this, I can see why this might trip you up because you see like the ring and you're like, this is pretty functional. The thing is it has nitrogen. So this is not an ether. This is another like nitrogen derivative. Maybe like an amine or something like that. But it's not an ether. It's not important. And then you get to this and you see, wow, I see exactly what we drew earlier. We have R, let's do it underneath. R, O, R. And these R's are just carbons, by the way. R is just carbon / alkyl groups. So this looks just like an ether. I'm going to circle this and move on. Okay? So it's very good to write out at the start what you're looking for, ether. The other ones you might see are, let's just review all the things that you might see here for safety. Let's bump up a little bit. You might see thiol. Okay? Thiol is just RSH. You might see ester, right? Which is just R double bond O, OR. You might see carboxylic acid, and we'll see this later too. Carboxylic acid. And this is just R, and this has got to be an H. So note the tiny difference here between these two. This is an R, this is a H. Small difference, okay. What else can you see? You might see alcohol, right? But alcohol is OH. That's just going to be ROH. And I think that's the extent of what you'll see for like the identifying problems. So just be careful. And be very careful with the thiol, okay? Thiol is not RSR, okay? This is not a thiol. This is not. This is, okay? So let's put like a X on this arrow. right? This is not a thiol. Sorry. And this is not. Let's be very clear here. This is not a thiol. Please, please don't make that mistake, okay? Not. This is, though, on the right. This is, okay? But yeah, so that's how you find the ether, okay? Very good. Okay, now we're going to go on to the next one. Circle the only chiral compound. Be very careful. It wants you to circle the chiral one, okay? Make sure you know what you're looking for. So chiral compounds, let's write out what we're looking for. We know that if there's a plane of symmetry, immediately, we are in achiral territory, okay? Achiral. And that's all you need to answer this question. So, all we got to do is look at our compounds and find the one that does not have symmetry, okay? So you might be tempted in this first one to sort of look and see that, okay, this is dash, this is wedge. So if I cut it this way, you know, there's an H up here and a BR down here, so it's not symmetrical. But just think about it as if, like, if this was sitting on a plate, okay? So let's draw on like a little plate. So we have a plate here. And these hydrogens, they're flat on the plate. So these are just like flat on the plate, like this, flat. These are going up and down the plate, okay? So hopefully that helps you visualize what's going on here. These are physically moving off the plate, whereas these are kind of like sitting on your plate. So these are on the plate, and this is up and down the plate, under, okay? So imagine now, if we cut this vertically, so if I grab a saw or a knife like this, and I bring that through this compound this way, that means that on one side, I'm going to have one H on the plate, one H on the plate. So this is symmetrical. This part is symmetrical. Here, if I cut it vertically, right, I'm going to have half the BR on this side and half an H on this side. Like I'm slicing through the middle of them. It's very hard to visualize this. But imagine I'm cutting it like this way. Like I'm going at them with a knife this way. Or not a knife, that's kind of, let's say like a sharp tool. Yeah. You're just cutting the compound this way. So that means that half the BR's on one side and half the BR's on the other side. So this is actually symmetrical. So this is not going to be the answer because we know if there's a plane of symmetry, that's achiral. So that's wrong. Number 2, we're going to skip it and come back to it. Number 3, this one's a little easier, okay? Recognize that if I do the same trick, right? If I put a plate here, right? So I have a plate, and now this stuff is flat on my plate, flat, and this stuff is going up and down my plate, okay? If I simply just cut this like this, look on both sides of my plate, okay? On the left side here I have an H, on the right side here I have an H. On the top I have a BR, on the bottom I have a BR. So this is like perfectly symmetrical. So this is wrong. Okay, and then we're going to get to this one. And this one I can see why it would be tricky. Because you would think that since this carbon has different groups attached, it's immediately chiral. But let's just be careful and draw our plate in, okay? So we have a plate like this. Right? And this stuff is on the plate, in the plane of the plate basically, and this stuff is going under and above the plate, okay? So hopefully that drawing is clear. Like this is going off the plate vertically, and this is going under, okay? But basically imagine if I cut the plate in half. So if I put a sharp tool here, and I cut the compound like this, like I cut it this way. So I like take this plate right here and cut this in half this way. That means that I would have half my BR on top, right? This one would be up here, and this would be down here. And then I'm going to slice through the plate. So I'm going to like cut half of the BR down and half of the H down. So that means that, you know, if I cut the plate in half, above the plate I'm going to have half a BR, and below I'm going to have half. You really got to visualize like we're cutting it this horizontally, but these things are horizontal. These are vertical, up and down. This stuff is on the plate flat. So that's why when you cut it in half, half is going to be below and half is going to be above. So there will be symmetry. So this is not the answer. So by process of elimination, this is our answer, but let's explain why, right? So if I draw on my plate again, and obviously there's a bunch of different ways to do this, okay? So if you have a way that you like to do it, just do it that way. Yeah, don't feel like you have to do it this way. But basically imagine now, right? If I were to cut this plate in half like we did in the last example, like we cut it this way. So that means that this BR would get sliced in half and this would all get cut in half. Recognize that, okay, on the left side, half the BR is above, half the BR is below, half the H is above, half the H is below. But on this side, my BR is above and my H is below, right? So these groups are not symmetrical. So that's why this would be chiral. I would say this was also on an old test. So make sure you practice this question. And if you're stuck, then you can message me, I'll help you. But that's as far as that problem goes. It's all about, visualizing it and then cutting it. So hopefully that's good. Okay, next question says, circle the only compound that will not react with the Grignard. So it's always important to know what you're looking for. So let's write out what will react with the Grignard. So Grignard, right? What is this thing? It's a strong base, right? Meaning what? Strong base, so it's going to attack any acidic, and it's important, they're acidic hydrogens. That could be like OH, NH, SH. And yeah, that'll be like the extent that you see. And then Grignard is also very, very strong nucleophile. And what do strong nucleophiles generally attack? Well, how about carbonyls? So things like this, where you have the partial, let's go a little smaller, where you have partial charges, right? We have a partial positive, partial negative. So the Grignard, what it'll do, if you remember, is it'll attack the positive and swing that to the negative. So if you know what the Grignard does, then you know what it won't react with. So just keep in mind, acidic hydrogens, it will attack. Carbonyl groups, it will attack. That's just characteristics, because the Grignard, what it is, it's like CH3. Oh, that's kind of messed up. MGBR. And then this is like a trick for you to remember, but this is not actually how it works. But if you want to think of it like this, like chemically, this is not fully, real. But if you're really confused on a Grignard, just imagine this whole group here. This thing is like a plus charge, okay? Again, this is not like the chemistry. This is like for you to remember. And imagine this is CH3 minus. So, minus charges on a carbon are one of the strongest bases because the electronegativity is so low. So it's very basic. And then since it has a full minus, it's also a good nucleophile. But again, this is not the chemistry, okay? This is just a little trick. So this is not the chemistry. It's just to help you remember, okay? So all we have to do here is circle the one that it will not react with. So let's go through it one by one. First one, I see an OH. This is immediately, I'm writing on my paper like this is acidic hydrogen. And the Grignard, like we said, is a strong base. So it's going to attack that. So the Grignard, what it's going to do is, I'll just draw this out for you guys. It's going to attack and deprotonate this, like this. Like that, and then that's going to go there. Okay, same thing here. I see I have another acidic hydrogen. So it's going to be the same mechanism. It's going to be CH3MgBr. And this could be any Grignard, by the way. I'm just using CH3 because it's the tiniest one that I know. But yeah. But it will attack these. So moral of the story, this is not the answer. This is not the answer. Here, okay. This is where you might be a little bit like, the Grignard might not attack here, right? But recognize that this is a carbonyl, right? So if you draw in your charges, right? If you do your charges like this, partially positive, partially positive, partially negative. The Grignard, what it's going to do is it's going to just attack this. Let's draw that more clearly. It's going to attack this and kick that there. So that's a reaction, and this is not the answer, right? Okay, and then same thing here. You see the Grignard, it can attack this partial charge here, right? So this is partially positive, partially negative, and this is due to the electronegativity difference of carbon and oxygen. So CO bond is polar, O more electronegative. So that means that it'll have the minus, partial plus, if you're confused about that. But yeah. So what happens here is same thing, CH3 MgBr. And it'll just come in here, attack that, and kick that there, right? So again, this is not the answer. This is wrong. Okay, so then by process of elimination, you know this is the answer. But let's just draw in our hydrogens, right? So we have H's here. Well, let's be consistent, actually. H. So, whoa, what happened there? You would think that like the Grignard is a really good base, right? So it'll attack these hydrogens. Only problem is these are not acidic hydrogens. Carbon-hydrogen bonds, CH bonds, are not acidic. Like this is not acidic. Because the electronegativity difference between these two, En difference, it's too small. Okay? So it won't react here. So this is our answer. This is the answer. The Grignard won't react with this. But another way I can see him asking this question is, circle the compound that will react with the Grignard twice. And so this is kind of like, you got to know what reacts with the Grignard twice. And I'm going to draw it out for here. So there's two things that react with Grignards twice, okay? And you must know these, because if this pops up and you don't know it, you might be confused. So the two things are, this is what we call, well, first of all, let me write out the question. So react, what does it react with? Grignard twice. So be very careful. If you see this question stem, okay, react with the Grignard twice. You gotta know that there's only two groups so far that you know can react with the Grignard twice. And those are esters, like this. So esters. Or acid chlorides. So these groups will react with the Grignard twice, this one and this one, okay? So just know that in case it pops up, you don't want to be missing that question, okay? This is also called like acyl chloride, if you're interested in that nomenclature. But yeah, that's the first page done, and it looks kind of messy, but hopefully it makes sense. Okay, so moving on to question 2. Wow, that was only one question. It was a lot of points. So let's explain the large difference in the boiling points of the two isomers shown below. Support your explanation with an illustration of the involved intermolecular forces. So he's kind of hinting at you here that you need to draw something for him to see so you fully understand it. The good news is you get to see what the boiling points are. So he gives you this boiling point and he gives you this boiling point. So you know that this one has a higher boiling point, okay? Excuse me. So higher boiling point, what does that mean about intermolecular forces? Does anybody know? Hopefully you know that. Let's write this out here. As your boiling point goes up, it's because your intermolecular forces IMF, also go up. So the more intermolecular forces you have, the more your boiling point is, basically. Because think about it, right? If you have a lot of forces in a molecule holding it together, think of it like people holding onto a ball, right? So that ball is like the molecule. Let's say we have 5 people holding onto this ball, right? Is it going to be easier to pull that ball away compared to a ball with only 2 people? Which one of these you think is easier to snag, to grab? This is going to be much more difficult to grab as opposed to this, because this only has 2 people holding it in place. So moral of the story is, the more forces on a molecule intermolecularly, the more difficult it is to break it. So that means that the boiling point is going to be higher, because it's going to take more heat to break this compared to this, if that analogy makes sense. So all you have to do is explain why this one is higher than this one, right? And so I hope you recognize that in boiling, there's a specific type of bonding that is often tested, especially in organic 1. And it's called hydrogen bonding, okay? So let's do a little run through of what this is. Hydrogen bonding, right? And that's when you have H's bonded to, does anybody know the atoms? F over N, okay? So if you have trouble remembering this, just think of it like hydrogens like to have fun, right? Hydrogens like to have fun. So all that means is that if there's a hydrogen bonded to one of these atoms, it can engage in a special type of bonding called hydrogen bonding. And that's stronger than, your normal bonding types, which is like, dipole-dipole, or what is the other one? Van der Waals or London dispersion. So all you got to do is explain why one of these has hydrogen bonding. And basically what you have to do is draw how the hydrogen bonding works. So for this molecule on the left, you notice that there's no H's on this O or on this N. There's no H's. So this guy has no hydrogen bonding. No H bonding. And that's kind of sad. Then you come over here and you see this one does have hydrogen on an H, right? You see that? So that means that this thing can engage in hydrogen bonding. So what you need to draw is what the hydrogen bond looks like, right? And so this is where you kind of need to know how to draw this out. But basically it's like this. And this is what he would expect you to draw on the exam as well. But this hydrogen can then, engage in hydrogen bonding with another molecule of itself. And that would look like this. Hopefully you've seen this in Gen Chem as well. But like this H, it would be like, you can just kind of draw this dashed line here, something like that. And then you can draw another one up here. This should suffice. All this is showing is that in the molecule, in a flask, there's a bunch of these molecules. And so whenever they come near each other, they can engage in this hydrogen bond between this O and this H, okay? And so all you got to write then is this can hydrogen bond as seen. And this one we already said cannot, okay? To really hammer this idea though for you, because that might be unclear, imagine you have a flask, right, of A and a flask of B, okay? What did A look like? A was something like, I hope this is right. It was something like this, I think. This, like that. And then B was something like this. And then the N was here and the H was here. So basically inside of these flasks, let's say there's like 100 of these. So let's say there's more like this. And there's even more. The only issue is, since this hydrogen is not bonded to F over N, and there's no F here, right? So we can eliminate that. But since it's not bonded to F over N, there's no hydrogen bonding going on here, or like hydrogen bonding going on here. That's not happening. So these are kind of just sitting there. interacting through like dipole-dipole, or like you can like van der Waals, but it's not important. There's no hydrogen bonding, London dispersion, blah, blah, blah. But here, if you look at this molecule, right, and we're looking at a flask of it, and there's a bunch of these floating around. That shouldn't be H. This should be H. Let's erase this. Like this, right? So if you draw in the hydrogen bonding, you recognize that this hydrogen is bonded to a nitrogen. So this thing can hydrogen bond everywhere. So this thing can like hydrogen bond here, and this one can hydrogen bond here, right? Like this can go like this. And so do you see how like there's these new forces involved? There's this like invisible red dash force. So that's going to increase the boiling point because, like I said up here, there's more hands on the molecule now, right? So think of it like that. And then obviously you got to write this out, hydrogen bonding, and then you got to draw this as well. So let me just outline the stuff you must have. So anything in red here, you got to have on your paper. You got to have this. Let's do a different color, actually. Let's do orange. Anything in orange, you have to show to get full points. You must show something like this, and you must show this fact. And you must write this, okay? If you do these things, 1, 2, and 3, then you should get full 30 points, okay? Full points. But yeah, that's all for this question, okay? So we can move on to another one. And let's look at this mechanism problem, okay? So propose a reasonable mechanism for the transformation below using curved arrows. You do not need to draw transition states. Let's underline that. Good. So let's look at what we have, right? We have an alkene, right? This is an alkene. And this is HBr. So does anybody know how HBr adds on an alkene, right? You have to know if it's anti-Mark or Markovnikov. But if you know the mechanism, it should make sense as well. But it's going to give you Markovnikov addition, basically, unless you have peroxide, okay? So let's write that on the side here, just to be clear. If you have HBr with the peroxide, this is very, very special anti-Mark, okay? But if there's no peroxide, like if this is not here, then it's just Markovnikov, okay? So in this case, we don't see peroxide. There's no ROR, peroxide, etc. here, right? So this is just going to be Markovnikov. But anyways, we need to show the mechanism. So the first step is identify the nucleophile and the electrophile. So is this H going to attack this double bond? No. The double bond is a nucleophile. It's high electron density. So it's going to attack, and let's draw this out clearly, like this. HBr, right? So this double bond is going to attack the H and leave the Br, okay? So then the next thing you got to do is draw what we just made, and let's do an arrow like this, right? And let's draw this next thing out. So we have like this, and this, and this. Uh-oh, what happened? And this. And then decide where to put the H, right? So since it's Markovnikov addition, we're going to put the H, we're going to put the H basically right here, and then give a plus charge. Oh, it's not drawing. Let's put the plus charge here, and the H is going to get added here, like this. But you don't need to show the H being added, where it goes. It's kind of implied that that's where it went since you put the plus charge, okay? So let's erase this, and let's draw this a little clearer. So this is plus right here, okay? So now you're gonna look, right, and look at your structure and recognize that, okay, I need to expand my ring somehow because I start with 5, so boom, 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 and I end with 6, right? So somehow I need to make my ring bigger, and the only way to do that is through the ring expansion. So this is where you might, get a little lost. So be very careful and just number your carbons, okay? Number your carbons. So let's number this. 1, 2, 3, 4, 5, 6, 7. And you see on carbon 5, there's a methyl. This is like a methyl. But just keep that in your mind, okay? So we know we need to make this ring into 6 carbons, and we know there's a plus charge. There's a plus charge here. So all you got to do is swing open your bond, okay? So let's just swing this here like that, okay? And that's going to make our 5-member ring into a 6-member ring. So that's going to go into a 6-member ring. So just draw your ring. You don't need to worry about substituents right now, okay? Just draw the ring. And then what stayed the same and what changed, right? So let's number our carbons again. And this is, again, just a good strategy to have. So this is still carbon 1. This is still 2. This is 3. This is 4, right? Now, here's where it gets tricky. You would think this is 5, right? The only issue with that is this bond between 4 and 5, we broke it. So this is not 5, okay? Carbon 4 is now bonded to something else. The bond between 4 and 5 broke, and it went to form a bond between 4 and, what is this? 6. So that means that this here is actually 6. And then the the bond between 1 and 5, we didn't break that, right? That stayed there. So that means that this carbon 1 has to be bonded to what? What is this? This got to be carbon 5. Okay? And then another way to check this is, look at this, right? This is carbon 5 here, and this is carbon 6. This bond between 5 and 6, we didn't touch that. This bond between 5 and 6 still exists. Does that make sense? Hopefully. So that's the numbering carbon strategy. And then, don't forget substituents. So carbon 5, you see it had a methyl here. So don't forget that. That has to come here too. So as a methyl. Oh, sorry. As a methyl here. And then carbon 6, it's attached to carbon 7. So we need to draw a line to carbon 7 like this. Carbon 7. Oops. Let me just fix this all, actually. Make that. Let's do this like that. Where is it? Okay. Yeah, so what was this? This was 6 and this was 7, right? Okay. So now you think we're all good, right? We're all good. The only issue is we need to put a plus charge somewhere, because this plus charge didn't just disappear. You have to conserve your charge unless you react with something as like a nucleophile electrophile, okay? So this is another tricky thing where you need to identify, okay, what lost a bond and has a plus charge right now. So recognize that either 4 or 5 must have a plus charge, okay? So let's just look at them, right? In the original structure, 4 is connected to 2 things, meaning it has 2 hydrogens, okay? So 4 has 2 hydrogens. So let's draw those in. 4 has an H here and an H here. Here, it also has an H here. Oh my goodness, it looks so ugly. Okay, let's get that out the way. This is carbon 4 still. 5, on the other hand, you see 5. In the original structure, 5 is bonded to how many hydrogens? 0. 0 hydrogens. So that means down here, we didn't just magically add a hydrogen, right? 5, this carbon, is still bonded to 0 hydrogens. So that means that this carbon has 1, 2, 3 bonds. So what does that mean about its charge? If it has 3 and it wants 4, it's got to be plus charged. Okay? Hopefully that made sense in terms of charge distribution. Another way to think about it is the bond between 4 and 5 broke, right? And 4 bonded to 6, which means that 5 kind of got left lonely. It lost a bond, right? You can think of it that way too. Whatever helps you. Okay, so now we have the charge saved, and then let's just look at what we need to form, right? So we need to form this like bromo dimethyl, whatever. So we need to attach a bromine, and the best way to do that is to use this Br- that we formed earlier. So all we got to do now is draw a nice arrow to this. Not in red, sorry. let's just react this with Br minus. We formed that in the first step. So this is just gonna go attack that empty orbital. Okay? And that would be the whole mechanism, basically. And you should get 50 points for that. Okay? So what is that? 1 page, 2 pages done? Okay. Next question. Propose a sequence of synthetic steps that would efficiently accomplish the conversion shown below. Show all the starting materials and the necessary reagents, but do not give mechanisms. So this is just no arrows, okay? So this looks super weird. We lost carbon somehow. Yeah, you might be really confused at this. And me too, looking at this. But let's just break it down step by step, right? So what do we know we can form alkanes with, right? We know that if we work back from an alkane, and we have a double bond here, so we need to think about that too. But if we work backwards, right, and we take an alkene, right, let's say there's an alkene, and we use H2 on like PT or PDC, that will reduce the alkene to an alkane, right? So that's interesting. How do we form alkenes? There's a few ways, but we can do an alkene by like, oh my goodness, I cannot draw a thing. But we can form an alkene from like an alcohol, right? And how would you convert that? But let me just change the color real quick for it to be more clear. H2 PAT. Well, you can do this with any acid and heat. So, not plus, sorry, and then heat. Or you can just use H plus as an acid and heat. Or, actually, yeah, that's good. So that's the way to make an OH into a double bond. Okay, so we're kind of getting somewhere. Then how do we make an OH? Well, we know we can reduce. Oh my goodness. We can reduce a double bond O, right? There's a few ways we can do this. You know that NaBH4 does this, or alternatively, LiAlH4 does this, right? And this is where things get a little tricky, okay? How can we get a double bond O, right, using this? And this is actually a one-step process. If you remember, what is the reagent that cuts double bond O's in half? And double bonds and puts O's on both sides like this. And that reagent is called O3. It's ozonolysis basically, O3. And then you must use like, I think it was CH3 2S. Yeah. You should couple it with this as like a solvent. But that would effectively do that. So this looks like a pretty good synthetic route you can take. If you worked from the front, you might be a little bit confused as to how to, maneuver with this. But honestly, retrosynthesis for me is a little easier. I do feel like it makes more sense as you flow through it. But if you feel like that, you want to start here and move this way, you can absolutely do it that way. Like, I'm not going to tell you how to do it, but just do it the way you're comfortable. Yeah, but this will effectively convert this into that, this into this. But yeah, let's see. What are some other things that you need to know about this synthesis? You might be tempted to do like bromine. So like maybe you did, like if you're confused as making the alcohol into the alkene, you could have done like, let's do it in orange, like a different route. You could have still made this into this, right? OH using NaBH4 or LiAlH4, right? That would still do that. And then you could make this into bromine, Does anybody know how to do that? Very good, PBr3. And then you can eliminate this into this using another reagent that we talked about a bunch. And that's what? Exactly, terbutoxide. So if you are kind of confused on how to do this acid catalyzed, elimination, then you can do this bromine route as well in orange. Both of these are effective. And you should get full points for both of these. Yeah. So that's like, 50 points here? Yeah. Okay. So that's it for the synthesis. If you're really confused, you can message me and we can work through this. But let's move on to number 5. So number 5 is talking about the organic compound is characterized by IR bands. So this is like you're moving into sort of like spectroscopy. So let's just write that out. Spec, like IR, NMR. So let's see what they say. There's an unknown compound with strong IR bands at 2930 and 1712. Okay, so this is already highly important. Okay, and then the HNMR. This is like the most important thing ever. So pay very close attention for every word they say. 3 peaks, okay. 1 singlet for 9H. So let's just write this out. So we have 9H, singlet, doublet, 6H, 6H, doublet, septet, wow, 1H. And this is all what? H1 NMR. And then the carbon-13 NMR has 5 peaks. So, C13. Oh, this one should be on the other side, my bad. And 5 peaks. So that means that there's 5 distinct carbon environments. Okay. So the first thing I would do is kind of work through the IR real quick, because that's generally the easiest thing to piece together. So if you reference your sheet, right, you'll know that IR, let's move to blue now because we're in the problem. So IR at 1712, reference the paper, and the paper is going to tell you it's acetyl-1O. Let me see if it's on here. Yeah, perfect. So we know we're at about 1700. And so it could be, some kind of ketone aldehyde, not really ester, definitely not amide, because you see amide is 1650, so it's not that. But it could be either of these, basically. So just keep this structure in mind. Okay. And then the other value was 2930. So let's look for 2930. So it's going to be about 3000. This is above 3000, so it's not an alkene. Okay. Because this says above. We're looking for 2930. This is absolutely below 3000. So this is an alkene. So keep this structure in mind. Yeah. So let's go back up here and let's write down. Yeah, so this is something like this, right? And then the other one at 2930 is something like just, carbon hydrogens. Okay. Then let's work through the NMR. So NMR is telling you we have 9H singlet, 6H double. Okay. So NMR, you have a 9H singlet. So what does this mean? It means you have 9 hydrogens equivalent contributing to a singlet. Okay, now we have to break down what is a singlet, right? So singlet means n plus 1 equals 1. So n equals 0. So no neighboring hydrogens. Okay. So the only way that this structure will ever exist, a 9H singlet, ever, is you must have 3 CH3s bonded to a carbon with no hydrogen. That can't be a hydrogen, right? So this is like some some group here. Because think about it. This is 3, 6, 9 hydrogens, right? So that's 9H. And it's a singlet, meaning this carbon here has no hydrogens on it because this is the neighboring carbon or the adjacent carbon. So N must equal 0, meaning that this must have no hydrogens. And that actually looks good. So whenever you see 9H or even 6H, be on the lookout for like CH3 groups like this. Okay, so that's the first signal we kind of broke down. Let's do the next one. The next NMR was a 6H doublet, right? So we got a 6H doublet. So what does that mean? That means that we have 6 hydrogens. Let me zoom out a little bit. 6 hydrogens contributing to a signal with 1 neighbor. And how do I know it's 1 neighbor? N plus 1 equals 2. So N equals 1. So that means that there's 1 neighbor. Let's just make this connection because of this, right? So what does that mean? Let's draw out some structures possibly. So we know we need to somehow do 6 hydrogens. So we can do that in a few ways. We can do like maybe like CH3 bonded to a carbon, right? And CH3. And since it's a doublet, this must have an H on it for 1 neighboring hydrogen. And then this can be bonded to something else. Or it could be, since it's 6 H's, right? It could be CH2, CH2, CH2. Bonded to like weird stuff on both sides, right? The only issue with this is, if we look at the splitting of these hydrogens, so let's look at this hydrogen. This is H2. Let's just look at one of them because they're equivalent. This H has 2 neighbors. So what's the splitting? N plus 1 equals what? N plus 1 equals what? If we have 2 neighbors, 2 plus 1 equals 3 triplet. So it physically cannot look like this. The structure cannot look like this. Like this would be wrong. But if you come over here and look at these, right? Look at these signals. So we see we have 3 H's here, 3 H's here. So 6 hydrogens. Let's just look at this one, right? So H with 1 neighbor. 1 neighbor means N plus 1 equals 2. Because N is 1, so 1 plus 1 equals 2. So this would be a 6H doublet. So that confirms that this is like, this is a piece. This is another piece right here. Let's put a box here. Actually, I wouldn't put a box just so it doesn't look like your final answer. But just keep in mind that this is the right answer for this. And then this is another piece. And then the last NMR we need to do is, let's kind of split this up, is, what is it, 1H septet, yeah. So we have a 1H septet. So this means that we have 1 hydrogen contributing to a signal. And then septet means N plus 1 equals 7. Therefore, N equals 6. So 6 neighbor H's, okay? So all we got to do is draw out what this would look like. So we know we have a carbon with 1 hydrogen, okay? Because it's a 1H, so CH. And then we know it has to have 6 neighboring hydrogens. So the only way to do that is you can do CH3, CH3, or you can do CH2, 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 H like this, right? Because this would mean that you have, what, 2, 4, 6 neighboring hydrogens. So you might be tempted to do it like this, right? And the only reason that I would say you can distinguish between these two is look back at your other piece, right? So if we look at this, right, and we compare it to this, what do you notice about these two? They're the same, right? So this is what you call like confirming signals, or like reinforcing signals. Basically, this one on the left here shows you something like this. And then you use another signal, a confirming signal, or like a reassuring signal, 1H septet. It could look like this or this, but odds are it's going to look like this, because this and this confirm each other. They're the same. So that's why you want to kind of go with this pattern. Yeah. And then also, if you do this way, there'll be issues with the carbon NMR, but you don't want to go that far and restart. So just kind of, logically assume, or it's safe to assume that this is the structure, because this and this reinforce each other. So then the next step is put it all together, okay? So we got one group here, one here, we got two here, and then this is the same group, just reaffirmed, right? So let's draw it all out in the middle here, kind of. It's really, really messy, but it's fine. Let's work in this space here. So let's work here. So we know we have a CH3 bonded to a carbon. And then this is bonded to something. And then we know we have a CH3 with an H on it. And this is bonded to something, right? Because we need to fulfill the octet rule. So this is where the carbon NMR comes in handy. Recognize that this carbon and this carbon and this carbon in the carbon NMR, they're all going to give off one signal. So this is carbon 1. This carbon is going to give off a different signal, carbon 2, right? This carbon here is going to give off a different signal. So this is carbon, 3? And then these two are equivalent. So these are going to give off one signal. So this is 4 and this is 4. So that means that we're missing a carbon somewhere, right? We need to add one carbon, one distinct carbon. And then also look at your IR, right? So in the IR, we know we need to add a carbonyl, this structure. So if you piece it all together, right, you kind of just gotta slap a C double bond O right here. And that would be the answer. And this would be the 5th carbon signal. And this wouldn't change the hydrogen splitting at all, because this carbon doesn't even have hydrogens, right? There's no hydrogens here. So it wouldn't change the splitting for anybody. And so this would be the answer right here. Like that. So that's how you do this IR NMR type of problem. Yeah. So if you have questions on that, you can also message or comment or whatever, and we'll get to it. So now we're going to get to the reaction section. And this is kind of a big problem, 60 points. So you just want to be very careful with how you go about this. Like, you don't want to mess up here, right? So let's see what to say. Write the products of the reaction of the compound shown in the center with the reagents shown on the arrows. Make sure to include stereochemistry, okay? You don't need to include mechanisms. Okay, perfect. So we can just get started then. Let's move in the left direction. Yeah, let's move left. What happened here? H2, I assume there's a PT there probably. I think it got cut off when I downloaded the sheet, but this should be H2/PT. Yeah, so we'll just go through this one by one, like reaction by reaction, so you can see. So if we're moving to the top left, right, the first reaction of H2PT, that's going to take my alkyne all the way back to an alkane. But it's not going to affect the carbonyl. So H2PT, I'll write these all out for you. This takes alkene or alkyne to alkane fully, okay? You have to know that. Otherwise, you would get this wrong. So that's the first step, okay? Second step, when you react this thing with NaBH4, that's a mild reducing agent, right? So that's going to take my ketone to an alcohol, like this. So let's write that out for you as well. This takes ketone to alcohol, right? That's what we show in step 2. Now 3 and 4, this is kind of tricky, but these are like a little bit coupled, like a coupled reaction. And how it works is, first the Na will act as a counter ion for sorry, I just got a message. The Na will act as a counter ion for the O. And what I mean by that is it'll look like this, right? And this will suddenly become O minus Na plus. You don't need to know so much as to why that happens, but just know it does, okay? And then the fourth step, which is what we're going to put in the box, is when we react this with CH2, CH3I, recognize that this is what kind of reaction? This is like nucleophilic attack, right? So this minus charge here on this oxygen, like this, is going to attack this and kick off this. And so your product is just going to be like this. This. And then we add 2 carbons because this is 1, 2, right? So this is 1, 2. So add those carbons. And that's it for the first one, okay? So coupled reaction for like for SN2 type mechanism. Make sure you look over this 3 and 4 because this is kind of like, you might not be so used to seeing that. But yeah, that's how you do the first box, okay? So then second box, we are going to look at this R2BH on this alkyne. So you got to know that R2BH and NaOH / H2O2, this is coupled. So this is like coupled reaction. It's not like 2 steps. These things, I mean, it is 2 steps, but what I'm trying to say is like they do one thing, like, yeah. So what do they do? You should know that they take alkynes. So these two, they make alkyne. And more specifically, they make terminal alkyne to what? To an aldehyde. Okay. And then you can also know that if it was internal, this is like side note, internal alkyne to aldehyde. I'm so sorry, to ketone. Yeah, to ketone, not aldehyde. So since this alkyne is terminal, meaning that there's an H on this side, this is going to go to a, what, aldehyde or ketone? Aldehyde. So let's draw that out, right? So step 1. And on your test, by the way, you don't have to draw out like all these steps, but it's very, very safe to do so you don't mess up somewhere and make like a silly mistake. So it doesn't mess with the O or the alkane part, like those 2 pieces, but it does make this, like, how would I show this to you? Let's see, it would make this carbon would stay, this carbon would stay, right? And then it adds, so this carbon is here, this carbon is here, and then it makes this into OH, like that. Okay, and this, let's label these, right? This is 1, this is 2, this is 1, this is 2. So that's how it kind of works. Yeah. And then step 2, or I should say, this is step 1 and 2. But step 3 is our final step. Chromium CrO3. This is strong oxidizer. Right? Strong oxidizer. And what does this do? This takes aldehydes to carboxylic acids. So you recognize that this is an aldehyde? Well, not a timer, sorry. it'll take this aldehyde and it'll just turn it into a carboxylic acid. So the answer would just be like this. Oh my goodness. Like this. Like that, right? And that would be box number 2 done. Okay. So hopefully that makes sense. Here, the tricky thing is recognizing that R2BH, this is like an alkyne reagent, if you remember, like BH3, that kind of thing. But for an alkyne like R2BH, you need to recognize that this is like hydroboration of some sort, and then know that it's like, if it's terminal, it does aldehyde, and then internal it does ketone. Okay, so review those differences and make sure you know that. Okay, and then the last one on the left side is excess Br2. So this one you might be confused because excess Br2 on an alkyne doesn't really make too much sense. But if we draw it out, it'll make a lot of sense. So let's just go one step at a time. Right, so we have this O. Oh, sorry, it should look like this, and then boom, 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 right? And okay. Like that. And then you know that when you react this with Br2, right? It makes that triangular structure. Excuse me. So this does like this thingy. And then this will go. Wait, why am I messing it up? Yeah, okay, stop. Let me just restart. So this will go here, right? And this lone pair is going to come here. And then this is going to break this way. So that'll add 1 bromine, like this. Sorry, I don't know how that tripped me up so bad. Right? And so then we'll have like this structure as an alkene, right? So this will be an alkene with a Br, like this. It looks really weird, but it just adds a bromine there. So that's the first step. And then another Br will come through, and then it'll basically the Br minus you form will come attack and kick that off, and then you'll be ending up with something like this. And it'll be an alkene with Br. And it's important to know that this is anti-addition. So this Br will be here, and this Br will be here. Okay, so that'll be the first step. Like, that'll be 1 Br2 addition. So if it said 1 Br2, it would be this. But since it's excess, right, you do the whole process again of making the triangle structure and whatnot, like this. Like, this is going to attack here. And then this is going to attack here. And this is going to leave. And at the end of the day, basically, it does the same process as this. Like, it makes this ring structure. Then the Br minus breaks the ring. And all that ends up happening is you add another bromine to both positions. Let's go to the graph. So it just ends up looking like dibromination. Like, this thing gets 2 bromines here. Br, and then this one gets 2 bromines here. And then obviously make sure you keep your answer in the box. So we'll move that in a second. So you want to always, stay in the box. Like that. And that'll be it for that question. Okay, so that's the left side done. We can move on to the right side now. So we'll start at the top here. This is Li. I think it's glitched again from my download, but LiAlH4, 1, and then 2. Let's just erase this whole thing, right? So that's the first step, and then 2 is H+ / heat. Okay, so LiAlH4, what does that react with? It is actually going to be does anybody know? It's a reducing agent. So this is a reducing agent. and it's going to take ketone to alcohol. Okay, so let's see, do we have a ketone in our problem? We do. So the first step, right? So step 1 is going to be, let's go back to this color, right? It's going to be this thing, like this. And the alkyne doesn't get reacted with. This thing doesn't get reacted with either. But that turns into OH. This thing turns into OH. Okay. Then the second step, you should know this is like acid catalyzed dehydration, where you have an acid and heat. So any strong acid, and this is on your last test too, strong acid and heat with alcohol, that's going to be elimination. Elimination. Okay. And then you need to know, is it going to be like the two types of addition? Is it Hofmann or Zaitsev? And this turns out to be Zaitsev. Okay. So the final answer is just going to be this structure like this, with the double bond here, and then this is going to be still an alkyne. This is going to be still there. Okay. So that's all good. And that's that reaction done. So now we're going to move down to this next box. And this is saying you're reacting with Lindlar's catalyst. So hopefully you know that Lindlar's catalyst stops reduction at alkene. And I should say stops alkyne. So the first step is just going to be to turn the alkyne into an alkene. So let's draw that here, right? Step 1, let's make that alkyne into an alkene. So boom, 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 and then boom, boom. Okay, like this. And then this is still a double bond to O, and this is still this, right? Okay, so that's step 1. Now you look at step 2, you recognize that this is a Grignard. Grignard. So immediately you're like, where do Grignards attack? Grignard is going to attack at the ketone. So this thing is going to go, well, let's just draw it out like this for you. This is going to swing into this double bond and kick that up. So step 2 is just going to be the formation of this anion, like this. O minus, and then this is a new methyl group. And then step 3 is important. This is called the acid workup step. So step 3 is where the O minus basically gets to go ahead and grab a hydrogen back from this. So these electrons, they can just grab an H and then kick the H there. And your final answer is just this, looking like this, with an OH here, and then this is an alkene, and this is that. Okay? So that's how you do this next one. Yeah, hopefully that makes sense. And then the last box we have, so the last box we have on the reactions page is H2/PT, and then NaBH4. So what you need to know about H2/PT is this does not stop at the alkene. It goes to alkane. So key takeaway, Lindlar's cat is alkyne to alkene. You must know this. And then the other one is NaNH3. That is anti-addition of hydrogens. And Lindlar's cat, this is syn addition. Okay. Yeah. So NaNH3, anti-addition of hydrogens, and this also stops at alkene, by the way. Stops at alkene. Okay. Yeah, that's what you need to know. And then H2PT does not stop, so it goes all the way to the alkene. So in this structure, right, if we were to react this thing with H2PT, it would take this triple bond into an alkane. So let's draw what that would look like. So step 1, it would just make this thing into an alkane like that. This thing would remain there and that would remain there, because all we did was remove the alkyne to an alkane, okay? And then step 2, NaBH4, you should know that NaBH4 is a reducing agent. And this can take ketones to alcohols. So hopefully that makes sense. Make sure you know that, because NaBH4, LiAlH4, they're both very, very high yield reagents for this. So it's just going to look like this. That. And then that should be your reaction page done. So if you have questions about any of these, feel free to message me. But I think there should be good explanations. Yeah. Okay, so that's it for the reactions page. All we have left is a few more problems about spectroscopy. So at this point, you should be thinking, you know, look how many points spec is worth. 40, 30, 40, another 40 here, right? So what is that? 40 plus 40, so 80 plus 30, 110 plus 40, 150. So you got 150 points from spec. And your whole test is out of 400, right? So what is that percentage? That's like over 30% of your test is from spec. So please do not ignore that stuff. You need to know this very well. Let's go through these. Yeah. Okay. So this problem says, predict the mass spectrum of bromochloromethane. Specify the number of molecular ions that you would observe, their masses, and their relative ratios. Okay. So first step is to draw out bromochloromethane. Okay. So bromochloromethane, what does that look like? That's a methane, which is one carbon, with a bromine and a chlorine. And then you got to fill the other gaps with hydrogen. So the molecular formula is what? C2. Oh, no, sorry. CH2BrCl. Okay. So then you got to recognize, okay, whenever you see these two ions, not ions, elements, Br and Cl, your mind needs to jump to the fact that there's isotopes of these. Isotopes. Very, very, very high yield. This is going to be on your test, I can almost guarantee. A bromine and chlorine isotope. Okay. So bromine exists as what? 79 or 81. You got to know that. Okay. Chlorine exists. Oh, and this is 50%, and this is 50%. So 50% of the time you're going to have chlorine. 50% of the time is 79, and the other 50 is 81. Okay. And then for chlorine, it can be 35 or 37. And this ratio is a little more difficult to memorize, but just know that 35 exists at a 3-to-1 ratio, so 75% to 25%, okay? So all you got to do now is write out all the masses possible. So let's just do all of our isotopes possible. So if we treat carbon, by the way, always treat every atom besides bromine and chlorine as their periodic table mass. So this is just going to be carbon is 12, H is 1. If you got oxygen, that would be 16. If you got nitrogen, that would just be 14, etc. You only have to worry about chlorine and bromine, because I believe that's the only ones you covered in your class, the isotopes, the major isotopes. So all you got to do is just write out the masses in different ways. So let's go. We got CH2. Oh, my pen is messing up. Okay, CH2, Cl, Br. This is what we're working with, okay? So the first isotope we're going to work with is, let's say we do Cl. Why is it doing this? I don't like that. Cl35 and bromine 79. So then all we'd have to do is total our masses. So we know we have a carbon, which is 12, a hydrogen, which is 1, and there's 2 of them. We have a Br, and we're using the 79. And we have a chlorine, and we're using the 35. So when you total up these masses and you do the calculation, you'll get 128 grams, okay? And then you got to do the percentage or the likelihood that this isotope is found. So how do you do that? You simply take the probability of getting one isotope, so this probability times this probability. So what's the probability that you get Cl35? And the answer is, you're going to get it 75. Why is the pen doing this? 75%, and the probability of bromine is 50% of this isotope. So 128 grams, and the probability is 37.5%. Okay, now we're just going to do this again. So now let's say we do chlorine 37 with bromine 79, okay? So let's do the same thing. We have one carbon. Oh my goodness. Carbon at 12, H2 at 1, and there's 2 of them, so that's 2. Let's make this more clear. 2 times 1 is not 128. That's the total mass, okay? What else do we have? We have a chlorine 37 and a bromine 79. So bromine 79 is 79 grams. I should be putting grams here for clarity. Yeah, we're talking about grams here. This gram should go here, sorry. And then we have Cl 37. 37. And that's what? 37 grams. So when you total up this one, you're going to get 130 grams per mole. Okay, so this is grams per mole. And then similarly, we're going to do the probability. So it's going to be, what's the probability that you find Cl37? It's 25%. The probability that you find bromine 79 is that. So when you multiply these two together, you will get the probability to be, it's going to equal, I think, 12.5%. Okay. So that's that. Then we have more isotopes we can do, right? We can do, the next one we can do is Cl, let's do Cl35 with bromine 81. So we still have carbon at 12 grams. We have hydrogen 2 at 1 gram times 2 of them. We have a bromine 81. That's 81 grams. And then we have chlorine at 35, and that's 35 grams. So when you add that all up, you should get 130 grams per mole. Okay. And then do the probability of these numbers again. So 35 probability is 75%. And bromine 81 is, oh, sorry, it's 50%. Is my pencil dying or something? Let's see what's happening here. No, that's not the issue. Okay. 50%. Okay. So when you do those multiply together, you'll get 37.5%, right? And that's the probability, basically. Or you can call it, I think he calls it likelihood, but it should be the same thing, okay? And the last isotope we can deal with is 37 chlorine and bromine 81. Let's do the math here real quick. So the structure is the same. Carbon is going to be 12 grams. H2 is going to be 1 gram times, not 12, times 2. Bromine 81 is how many grams? Very good, 81. And then chlorine 37 is how many grams? Thank you, 37 grams. So that's going to equal 132 grams per mole. And then do the math here. This is going to be, what's the likelihood that you find 37 chlorine? That's 25% of the time. And the bromine likelihood is always 50%. So when you do these together, your probability equals 12.5%, okay? So that's all the math done, right? Now we have to interpret what this means. So whenever you have isotopes of the same weight and you want to do a mass spectrum, you are going to combine their probabilities into one big peak, because what the mass spec tells you is the weight of these ions. So mass spec down here, you're going to have the weight. So like 128, 130, 132, 134, whatever. Like this is the weight. So the probability that we get 128 grams is 37.5. The probability that we get 130 grams is these two added. And then similarly, the probability that we get 132 grams is just 12.5%. So now you just got to look at the ratio between these numbers. So this probability total, by the way, probability is now 50% because 12.5 plus 37 is 50. So now you just need to find a ratio, right? So the ratio here would be that 12.5. Well, if you have trouble finding ratios, this is kind of like some old math, but you just divide by the smallest number first and see if you get whole number integers. So divide that by that, you'll get 1. Divide 50 by the smallest number, which is 12.5, you'll get 4. And divide this by 12.5 and you'll get 3. So the ratio is 1 to 4 to 3 of these masses, because you want them in whole numbers so you can make your peak in whole numbers. I don't know if you write the percentages over the peak, if you'll accept that. Because technically you could say like this is prevalent 50% of the time, or this is prevalent like, 50%, 12%, 37%. But I think it's safer to do the whole number ratio math. So just find the ratio of what each probability is. So for every one of these, there's 4 of these, and there's 3 of these using algebra. So all you got to do now is move to your mass spectrum, right? And draw in peaks. So at the 130 height, this is 4. That's the ratio. At 132, the ratio is 1. And then at the 128, it's 3. So we're going to go up a little higher, like 3, something like this. And then at the 134, there should be nothing because we did not calculate an isotope that added up to 134. So this shouldn't even be here, actually. You can just eliminate that, okay? And that would be your answer. This would be like the mass spectrum right here. Okay, we can circle it in a different color. Hopefully that makes sense. If you're confused on this, again, you can message me and we can work through another one. Okay? But yeah. So next question, this is also, some kind of spectroscopy. This is, we're using what? NMR, and we're given a formula. So let's see, a compound with the formula C12H12 shows 1 singlet and 3 double doublets in its HNMR, okay? Each of the peaks, integrating for the same number of hydrogens, propose a structure which is consistent with this observation. Okay, we can do that. So the first step is always going to be to get your degrees of unsaturation. So if you're given a molecular formula, let's get your degrees of unsaturation first, okay? So, how does the formula look like? It's 2C plus 2 minus H minus X plus N, where X is any halogen, all that divided by 2. So if we do that here, we have 2 times 12, right? Plus 2 minus 12 minus 0 plus 0, all that over 2. And that's going to equal 7. So immediately you see 7, right? And you got to think, since this is greater than 4, you probably have a benzene. Benzene is like probably going on here. So let's just draw in a benzene, right? And we'll start with that. And benzene is how many degrees of unsaturation? Does anybody know? It's 4 degrees of unsaturation. So now we got to add in some other groups to make it C12H12. So right now we're at what? C6 1, 2, 3, 4, 5, 6. H6. So we need to add in another we need to add in more C6H6. Okay, so the thing is now you only have one singlet showing up, meaning that in your structure, if there's only one singlet, that means that there's something bonded to the benzene, right? Here, let's say there's something bonded to benzene here. Let me move it down so it's more clear, actually. We'll make this more clear. Let's make it a little bigger. So if we have something bonded to benzene here, right, there's no hydrogens here, right? There's no hydrogens. So that means that whatever's bonded here is a singlet, okay? And so we only have one of them, but that doesn't make sense, right? Because if we only have one singlet, then we would have like way more hydrogen peaks. We would have like 1, 2, 3, 4, 5, right? So the thing is, this is hinting at you that there's symmetry in this molecule, basically. And so you got to recognize that since there's only one singlet signal, there's actually going to be a few of them, but they're all symmetrical. And that's kind of weird to think about, but hopefully it'll make sense after we do this. But basically, that is how you get a singlet, an X, okay? So just keep that in the back of your mind. And then we have 3 double doublets, okay? So 3 double doublets, what that means is if you have a hydrogen here, right? And we have like an X here, and we have a hydrogen here, and we have an X here, and let's erase this and say we have a hydrogen here, and an X here. Do you see at this signal, right? Let's see. Let me chop that actually. What am I trying to say here? Yeah, so basically we have 3 double doublets. So what we got to do is on our ring, recognize what does a double doublet mean. And a double doublet just means that there is a double bond, like a C, double bond C, like this with 2 H's, right? And this H here, and this is an R. So this is what a double doublet looks like. And there's 3 of these. So if there's 3 of these double doublets, right, that means that we need to spatially show these on our structure symmetrically, basically. So let's just show it like this, right? So we should do this, right? And then this, and this, and this, and this. So that'll be the 3 double doublets in the proton NMR, right? And they each integrate for the same number of hydrogen atoms. So that's why this is kind of characteristic. And then the one singlet, that's going to be from this this signal here. So this hydrogen here has no, this hydrogen here has no neighbors. So it's going to be a singlet. Yeah, and this is also a singlet, but this singlet and this singlet and this singlet are all equivalent. So that's why this is going to be the structure. The reason this is so tricky is because you have to know what a double doublet means. And if you don't, it's kind of difficult to answer this. But basically, if you have a double doublet, that's this thing here. If you have a triple doublet, I can show you what that looks like. So like this would be a doublet of a doublet of another doublet. And so that looks like, that would look like this, like C double one C, H, H, oops. This would be bonded to a C, and this would have another H on it. Yeah. And this would be bonded to more things. But you see in our case, our C is bonded to, like our double bond C has one H and is bonded to a carbon with no other hydrogens. Whereas this one, it does have a hydrogen. So that's why it's not a doublet of a doublet of a doublet. It's just a double of a doublet. But the vocab in this is kind of tricky. So I'm pretty sure you guys went pretty deep into detail about like double doublets, maybe even a triple doublet in class. So make sure you look over your notes, because if you don't know what that looks like, then this problem is very, very, very hard. But yeah. So this will be our final answer here. This will be the answer. Yeah. Right. And then we can also check for our degrees of unsaturation. This is 1, 2, 3. Right. So this is 1, 2, 3. And the benzene is 4. So 3 plus 4 equals 7. And we know that we need 7. So that all works out, right? Okay. Next question asks, how many peaks should be observed in the H NMR and C13 NMR of 3-fluoropropene? So the first step in this is to draw out what is 3-fluoropropene. So propene is 3 carbons, so 1, 2, 3, and then we have a fluoro, right? And you can just write F. And then it's a propene, so there's a double bond. So the double bond is going to go here, because when you number it, it needs to be like 1, 2, and then the fluoro is on carbon 3. So that's why the bond has to be between 1 and 2. So then all you have to do is just draw in all your hydrogens and label them as, you know, new or different. So this has an H here and an H here. This has one H here, and then this has H here and H here. So let's see, would these be the same or different, right? So these two would be the same, since they can rotate and, you know, flip. This one, since it's on a double bond, let's go to a new color, right? This will be new. And then last but not least, this would be new because it's on a double bond. And this would also be new because it's on a double bond. So since these are all on double bonds, they can't rotate freely, so they're kind of stuck in their environment. If there was symmetry across the double bond, right? If there was symmetry this way through this double bond, then these two would be the same. But since there's no symmetry, right, then these two are different. So just count your hydrogen types, right? We have 1, 2, 3, 4 hydrogen types. So we're going to call this, we're going to say we have 4 H signals, 4 H1 signals in H NMR, right? And then we can do the same thing for the carbon. So I'm just going to redraw it because it's kind of clunky over there, right? So let's just redraw this like this. And then like this, we have a fluorine here. So let's look at our carbon signals. So this carbon signal here, carbon, is definitely going to be different from this one because this has 2 H's, this has HH, and this has 1 H. So this is absolutely going to be different from this one. And this one has 1 H, whereas this one here has an H and a fluorine. So they're going to be different as well. So all 3 of these are going to be different. So you would observe 3 signals in the C13 NMR. Okay. And then it wants to know the splitting of these things, right? So to get the splitting, you would just look at so we're going to look at the proton splitting basically. So let's draw it again, just so we can do this very clearly and easily. We have this, fluorine, H, 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 like this. Like this, right? So the splitting on this, let's just go right to left. So this hydrogen has 1 neighbor, right? Like these two are equivalent, so n plus 1 equals 2. So this is a doublet signal here. So this would be like a 2H doublet, basically. But you don't need to include 2H. That's extra. Doublet. This one here in orange has 1, 2 neighbors, right? And then it also has neighbors on the left side. So these two, right? So you can call this like double doublet, triplet, because this would be the double doublet part, and then this would be the triplet. Or you can just say this is like multiplet. So this is like multiplet basically. Okay. And then these, right? These are different. So let's work on the one in black first. So it has a signal here. So this is an H, one H, so that's a doublet. And then also has this H, so a doublet, doublet. Okay. And then last but not least, we have this one in, let's do it in blue. So this one has one H here, so that's a doublet. And then it also has this H here in blue, so that's a doublet. So it's like double doublet. And this is also, you know, double doublet. Yeah, we can box in these answers like this. Okay. And then that's all this question asks, right? So yeah, what will be the shapes of the peaks? Okay, and then the last part, it says cyclopentadiene, shown below, is unusually acidic hydrocarbon with a pK of 16. Why would this happen, and show appropriate resonance structures? Okay. So acidic hydrocarbon means that the hydrogens are abstractable by a base. So let's just draw that out. So if this acts as an acid, that means that a base comes in here, base, and it's going to pull one of these off, right? And so what we're going to get is something like this. This minus, and this and this. Let's be more clear. This and this, like that. So the reason this is so stable is because you can just resonate this minus in so many places. So you can kick this here, right? And kick this here. And that'll give you a new structure. And that'll give you this and this with the minus here. And then similarly, you can just kick this here and move this here. Okay, and now we got another structure. So now we got this, like this. And this is minus here now. And then similarly, you can do it again, right? You can move this here and move this here. And that'll give you this. It'll be like this and this. And the minus will be here. And you can just keep pushing this all across. So just write yourself a little note, right? That basically, well, let's do one more resonance structure for safety. And that'll give you this. And this will be minus here. So all you gotta write is like high resonance, stabilization, and you can say something like delocalizes. I can't even spell. Oh my goodness. Minus charge all across ring. Oh my goodness. And then you just turn in your final, okay? Yeah, that's pretty much it. So if you have questions on any of this stuff, you can definitely leave a comment or message on the GroupMe or on Teams, whatever, and I'll get back to you. But other than that, hopefully, you know, everybody has a very, very happy Thanksgiving. Happy Thanksgiving to you all. Thank you for being such a great workshop, and, you know, hopefully you guys crush this final. But yeah, good luck. Thank you, and have a good day.